Welcome PCS members and friends to our today's Thursday PCS IBS seminar. It is a great pleasure to have with us today Dr. Sunghun Park from Autonomous University of Madrid. And I would like to invite our scientific host, Hichul, to introduce our speaker. Please, Hichul.
Thank you, Tilen. Today our speaker is Dr. Sunghun Park. I will just briefly introduce him. He received his PhD from KAIST 2011, and he stayed there 2 years more for the postdoc, and he became a BK21 research assistant professor there. And then 2013, he moved to Germany, the Technical University Braunschweig. And 2016, he moved to Universidad Autónoma de Madrid in Spain now. Today, his research interest is quantum transport in mesoscopic system, such as graphene, topological matter, and superconducting Josephson junction. Today's topics. Today, he will give us very nice talk. The title is Spin-orbit splitting of Andreev states in Josephson weak links. Okay, someone, screen is yours.
Yeah, thank you very much for kind introduction, and thanks for giving me this good opportunity to give a talk. So I think we have time for discussion later, but please interrupt me at any time if you have questions during the presentation. So here today I talk about the spin structure of the Josephson of Andreev bound states in a Josephson weak link, studied in these references. So I will start with a brief introduction, and we'll see the spin split Andreev states and how to measure these states in circuit QED experiment, as shown in this schematic figure. Finally, they will discuss about how to use these states as a qubit. So, as you know, the qubit is a two-level quantum mechanical system, and it's an elementary unit of quantum computer. So the most natural qubit is an atom. So its physical size is about 0.1 nanometer, and the separation between levels is about 0.1 electron volt. However, these physical properties that are not tunable, and it's not a promising candidate. So people have developed a so-called artificial atom in which we can easily manipulate the states by applying an electric or magnetic fields in a wide range of this microwave frequency. Here we can also detect these states by coupling this artificial atom to a C resonator. There are many examples for this artificial atom. For example, the flux qubit, the Cooper pair box, which they have a bosoning mode, and also the Andreev bound states, which are the fermionic modes in superconducting atomic contact or nanowire Josephson weak link. What I want to talk today is about this nanowire Josephson weak link. So this work is a part of the European project of the coordinator Attila Geresti, with the aim of scalable quantum, developing the scalable quantum computation using Andreev states. In this project, 8 groups that are involved, and here the nanowire material used in our experiment was made by the Copenhagen group, and the The work was done in collaboration of the theory team in Madrid, where I'm involved, and the experimental group at the Saclay in France. So basically, the Josephson weak link consists of the two superconductors, which are connected by a metal, for example, the atomic contact, nanotube, or nanowire. Here, data is the phase difference between the two superconductors. In this case, the electron hole at the interface between the metal and the superconductor, the electron hole Andreev reflections occur, and it forms the Andreev bound stage, which depends on this the superconducting phase difference delta. So superconducting atomic contact is one of the representative examples. Here, it can be made by the broken aluminum junction, as shown in A, and this structure has simply the two Andreev labels inside the gap, shown in the B. These energies are characterized by the tau, the transmission probability across the junction, and so in this system, the transition between these labels and their manipulation were reported experimentally already about 10 years ago, and these studies allow us to use the Andreev labels as a qubit, which we call this Andreev label qubit. In a nanowire, the Josephson weak link, the property is more complicated, and in this case, the electron dispersion relation affects the Andreev energies. So as you can see in this plot, for the thin nanowire, the simple parabolic dispersion relation is the good approximation as the theoretical model. In the presence of the spin-orbit coupling, the spin up and down bands are split, as shown in the middle. If we increase the thickness, the diameter of the nanowire, then the separation between the transverse subbands is reduced, and there's a hybridization between these different transverse subbands. Here, as you can see here, that compared to these dashed lines, which corresponds to the absence of this hybridization, it modifies this band structure. So if we zoom in this band structure around the chemical potential mu, then we see that this modification give rise to the different Fermi velocities, the V1 and the V2. This is actually the main mechanism behind for the spin split Andreev stage. So these plots show the Andreev energies for different lengths of the nanowire L with the realistic parameters. So here at equals 0, we see only the Andreev levels with the spin degeneracy. However, as we increase this length, more and more levels appear inside this superconducting gap, and the splitting between these labels become clear.
Sorry, can I ask something? Can you go back? So the L0 means just two contacts.
Actually, in this case, it's the same as the atomic contact. Yes.
And these contacts are just the dispersion that you showed on the left.
Yes.
Yes. Okay, thank you.
So yes, thank you for the question. It's a good point that actually this spin splitting appear only when the length of the nanowire is finite. So here, the expression you have shown in this right upper panel, this is the analytical expression for this Andreev energies that I obtained by solving by matching the wave functions at the normal nanowire and the superconductors. Here, the information about the different Fermi velocities, V1 and V2, is encoded in this, the lambda parameters. And we also have this the transmission probability tau and the XR, the position of the scattering barrier. So the expression is the useful to fit the experimental data. And I also want to remark here that the real spin degree of freedom, the real spin is not a good quantum number in this case because of the spin-orbit coupling. So here, U and D, what I'm telling you is not a real spin, but the pseudospin, which is defined by the product of the real spin, arrow up and down, and the transverse modes M1 and M2. So physically, the splitting is analogous to the fine structure of the hydrogen atom. You can see in this right panel. So for this region, the splitting of the Andreev stage can be considered as the fine structure of the Josephson weak link. So if you don't have the further question, let me go to the next part. So this is the schematic of the circuit QED setup. It consists of the two parts. The one is this the LC resonator of the frequency F1 and the superconducting loop containing this the Josephson weak link with the Hamiltonian HQC. Here, the flux phi enclosed by this the superconducting loop is it controls the phase difference delta of this the Josephson weak link. Here, they are coupled inductively, and in this case, the zero energy fluctuation of this the resonator induce the small fluctuation in this the phase difference delta. Here, denoted by the delta R. The strength of this the coupling delta GP is the different for the different experiment, but in our experiment is in order of the 10 to the minus 5. So to get explicitly the coupling Hamiltonian between the resonator and this superconducting loop, we do Taylor expansion of this Hamiltonian AndQC with respect to this induced coupling. So this is the coupling Hamiltonian we obtained by doing this expansion up to second order in coupling. Here, the first order coupling is already known as the James-Cummings model, and it has been studied intensively in the context of the circuit QED and also the cavity QED. The new term I'm considering is the second order coupling. So by solving this quantum mechanical problem, we get this shift of the resonator frequency, delta Ri, which is induced by the occupation of the quasi-particle at the level I in this Josephson weak link. Experimentally, we measured this shift of the resonator frequency, delta FR, and measured the stage of this Josephson weak link. So here's the solution for this resonator frequency shift. Here, the two terms come from this first order coupling, and the new contribution from this second order coupling is the first two terms. So let me show you this simply the two Andreev energies, the E0 and E1, as an example. Here, the E01 is the transition energies between these two levels, and I assume that the lower level E0 is occupied by this quasi-particle. So in this case, the blue dispersive region where the transition energy is similar to the resonator frequency, then the frequency shift is determined by this resonator frequency dependent terms. Actually, in this case, this is the result from this James-Cummings models, and in this case, the second order coupling term is negligible. However, if we are in this red, which we call the adiabatic region, where the transition energy is much larger than the resonator frequency, then this frequency shift determines by the curvature of the occupied level, and it's independent of this resonator frequency. So the expression I found can describe this frequency shift in a wide range of parameters, including this intermediate region between these dispersive and the adiabatic regions. So this is the main message of this part. So now let me give you some experimental details. Image A shows this aluminum indium arsenide, the aluminum Josephson weak link. Here, the indium arsenide nanowire has the length about 370 nanometers and the width about 140 nanometer. Here, through the side gates, we apply the gate voltage to control the carrier density of the nanowire, and also this AC microwave F1 to induce the transition between the Andreev labels. This weak link is embedded in this superconducting loop shown in this image C. And the loop includes the flux phi, which controls the superconducting phase difference delta of this weak link. And the superconducting loop is inductively coupled to the microwave resonator, as shown in this image D, and as shown in the bottom of the image D. Here, we send the wave with the frequency f0 along this transmission line, which is coupled to the resonator, and experimentally we collect the transmitted signal IQ and measure this absorption spectra and also the shift of the resonator frequency. So,
we have a question.
Yes, just some experimental precision. What is the substrate in this setup?
Yeah, in this case, the substrate, the silicon. Yeah.
And the technology is some lithography.
You mean that how to make this weak link?
Yeah.
I think this is I don't know the details, but this is epitaxial grown nanowire.
Wire. Okay.
Yeah. So the
okay. Thank you.
Yeah. Thank you. So here the plot in the middle shows the absorption spectra, what we expect when we shine the microwave on this spin split Andreev labels. Here the the red dashed and the solid lines indicates the pair transitions from ground to excited state, and the green solid and the dashed lines are for the single particle transitions between the spin split and the levels.
Can I ask you a question?
Yeah, please.
Don't you have spin-orbit coupling in the weak link?
Yeah, there is.
And is it taken into account?
Yes. Yeah.
In the Hamiltonian? Because I'm not sure that I've seen it.
Sorry, I didn't explicitly showed you the Hamiltonian, but the model I considered is shown in this slide. So
okay.
yes, the band structure I used is shown in this right plot. Here, I considered this the spin-orbit coupling Hamiltonian shown in this slide in this thick nanowire. Here in this case the diameter or the width of the nanowire is about 140 nanometers. So the separation between the transverse subbands is comparable to the strength of this spin-orbit coupling. So
I understand, but since you also have a magnetic field, as you said, 2 slides before, to control the superconducting phase difference, don't you have to take into account also the effect of the magnetic field?
Thank you for the question. In this case, in experiments, yes, this is the flux phi of the magnetic field.
Yeah.
Actually, controls the phase difference, but the strength of the magnetic field is about micro Tesla.
So you neglect it.
Yeah, it's really negligible. So I will show you the effect of the magnetic field later, but this is the effect of the external magnetic field, but not related with this magnetic field controlling this phase.
So if I understand you correctly, you assume that this magnetic field that causes the flux phi is smaller than the effective magnetic field induced by the spin-orbit interaction. If I understand
exactly, yes.
correctly. Okay.
Yeah.
Thank you. Thank you.
You're welcome. Yes. So let me continue. So here is the experimental data we obtained as a function of the driving field F1 and the phase difference delta. Here, although we didn't observe all these expected lines, but we see a bundle of 4 lines here corresponding to the single particle transitions. And it's the clear signature of the spin split Andreev stage. So using the theory of frequency shift I explained, and also taking into account the driving field effect, I calculated the shift of the resonator in the presence of this driving, as shown in this form, which is similar to this form equal to rule. So with this expression, I was able to fit this absorption lines and also the line intensity, which corresponds to this delta F1 shown in this expression. So we further considered the effect of the magnetic field to see the spin character of the Andreev stage. So in this case, this is the external magnetic field independent of the magnetic field associated with the phase difference. In this case, the order of the external magnetic field is about the milli-Tesla, but as I told you, the field associated with this phase difference is about 1 micro Tesla. So I focused on the spectra around delta equals 0 to see how they evolve with the magnetic field. So we applied the magnetic field along the nanowire and also the perpendicular to the nanowire, and also we changed the strength of the magnetic field. So here the green lines are theory calculations, and as you can see, the theory calculation provides the good agreement with the data. Yes. So finally, they comment about how to use these states as a qubit. Actually, this idea of using the Andreev spin as a qubit was suggested about 20 years ago. And the motivation is that this Andreev spin has the superconducting elements and also the semiconducting elements. So for this reason, this spin might take advantages of the superconducting qubits and electron spin qubits. And the goal of this idea is to make a qubit with this high controllability and the long coherence time. So specifically, we can use the one U and the one D, the two levels in this low Andreev manifold, as the basis of the qubit. This the UD, the pseudospin states, are represented by the 2 degrees of freedoms, the real spin, the arrow up and down, and the transverse modes M1 and M2, which is whose the spatial configuration is drawn in this lower figures. Here, in this case, if this nanowire has the transverse symmetry, then this M1 and M2, these two modes are orthogonal, and in this case, the two pseudospin states U and D are also orthogonal to each other, so that the transition between these two states are not allowed. However, if we break the transverse symmetry, for example, with the side gates, then there could be some overlap between these the M1 and M2, and it induced some coupling between these two pseudospin states. So in this case, we can expect some transition between these two states. In our experiment, we observed this transition between U and one U and the one D stage. Here I call the pseudo-spin-flip transitions. Here the red curves are what we expect, and if you see here there's a weak, but the signal is very weak, but we observe this transition between the two one U and the one D states. We believe that the side gates in our experiment breaks the transverse symmetry of the nanowire, and it induced the pseudospin-flip transition. Now let me summarize my talk. Here I have shown that the spin split Andreev states at the zero magnetic field, can be realized in this nanowire Josephson junction due to the combined effect of the spin-orbit coupling and the multi-channel structure of the nanowire. And also we observed the spin split Andreev states in the circuit QED experiments. and it could be used. The stage can be used as a qubit. However, in order to manipulate coherently the stage, we need more studies. So thank you very much. Thank you for your attention.
Thank you, Sun. Let us thank our speaker. A very nice and clear presentation, and we are open for more questions from the audience. Sergey, please go ahead.
Yeah, you mentioned the end of your talk, the coherence time issue of this Andreev spin qubit. Can you tell us some numbers and how these coherence times, experimental, I mean, coherence times compare to other qubit realizations or proposals of qubit realizations?
Yeah, thanks for the question. Here, first, some numbers I know for this the electron spin qubit. I think it's about 0.1 to 1 microsecond, and there's one experiment recently from the Michel Dvorak group at the Yale University. They measured the coherence time in this nanowire Josephson junction, having the spin split and the levels. And in this case, that they got the number 50 nanosecond, which is the
nanosecond.
Yes, 50 nanosecond. So still smaller, much smaller than the typical coherence time for the spin qubit. But I have to say that this is the experiment measurement for the first time. So I think it's early to say something. I think that the coherence time for this the spin split and the stage can be improved, but still this is the studies are in progress.
And is that also is the difference also similar when it comes to the Q factors, to the quality factor? Because I mean, I don't know what probably the energy scales are comparable, right? But anyway, I mean, are the Q factors similar also, or similarly different?
The Q factor of the resonator, or
yeah. Well, if you take a standard superconducting qubit, so what would be the maybe the total coherence time you said is maybe one microsecond, but what's the Q factor? Is it 10 to the 3 or 10 to the?
In our experiment, the Q factor of the resonator is about 10 to the 5.
Okay.
Yeah. I guess with this Q factor, probably the resolution of this lines is in the order of the megahertz, but I don't know the details. But as you can see, the experiments, the shift of the resonator is in the order of the hertz, extremely small. So I heard from this experimental group that normally when they do this measurement, they see nothing. So that they do some further further works to make clear the signal. But sorry, this part I don't know in detail, but to get this frequency shift from this collected experimental data, I and Q, there's some seems that there's some additional intermediate process from the experimental side.
And back to the coherence times. What are the reasons that they are currently, as you mentioned, they are what is it, like 10 to 100 times shorter than the standard?
Yeah, standard electron spin. Yeah, qubit.
What is the reason for this much shorter coherence?
I think that still the isolation of this Andreev's spin qubit is not so perfect compared to the electron spin qubit confined by this electrostatic potential. In this case, there is still sorry, this is the I don't have good answers about this. I don't know why there is smaller than that of the electron spin qubit. What I know is that it's very sensitive to the physical properties of the nanowire. When you change the gate voltage of the nanowire, or if you change the length of the nanowire, the properties sometimes drastically changes. So I think that at present, even this mechanism for this transition between the levels are not clear. So still, I think the theoretically and experimentally, there are many things to study. So.
Thank you.
Thank you. Thank you very much.
Maybe if I can continue on this question by Sergey. So I guess the important point is then one is coherence time, but the other is how many manipulations or gates you can apply, right? In how fast. So these two time scales, right? So yes. Is there, as you say, this is work in progress, but do you have some estimates that this could be done much faster than in, for example, the quantum dot, the electron spin qubits, or in these other schemes?
Yeah, also sorry, this case say that I don't know, there's a possibility, but still I don't know how can it improve this time for the manipulation. Yes, still, I don't have a good knowledge about this evolution of the states in this time domain. Yeah, so probably
Is the time scale related to the level splitting? I mean, the inverse or something like that, I guess.
Yeah, yes. And in this case, the lifetime, is affected by this transition from the quasi-particle from the continuum stage, and also it depends on how many Andreev levels you have inside the superconducting gap. What I'm working on these days with the students is that we already know some how what determines the quasi-particle lifetime, and also some time scale for the transition from ground to even for the short junction case. I say for the superconducting atomic context, but what happens and how these time scales change when you increase the length of the nanowire. This is actually the study that I'm working on these days. So still hard to say something clear. Yeah, sorry.
Okay, but, thank you.
If I have some better understanding about this, then we can discuss.
Okay, thank you. Do we have any other questions from the audience?
Yeah, can I ask?
Please go ahead.
Thank you for your talk. I understand that your talk was related to the spectroscopy, but can you measure Josephson current in your experiment?
In principle, yes, but we didn't. Yeah, we didn't measure the Josephson current.
Because if you have this inverse occupation of your Andreev level, so obviously you will affect the Josephson current, which is evidence of this. And the second moment, I think that when you have spin-orbit interaction in SNS junction, the manifestation of spin-orbit effects is that you can have Josephson current even in the absence of phase difference between two superconductors.
Thanks for your question. Thanks for the important question. Yes, you're right. For example, for the atomic superconducting atomic contact, for example, in this case, if you measure the Josephson current, then you get the zero Josephson current for the single quasi-particle stage case. You have some finite Josephson current for the ground stage, but if you put the additional quasi-particle, then your energy for this single quasi-particle is zero, and the Josephson current in this case 0. But in this spin split and in the case, this single quasi-particle stage, that the energy of this many body stage is not 0, and if you calculate the Josephson current is finite even at the delta equals 0. So you're right that from this we may demonstrate that there's some spin-orbit coupling or there's some spin splitting, between the Andreev levels. Yes, that's an alternative way to demonstrate that this spin splitting of these Andreev states.
Thank you.
Thank you.
Do we have any further questions from the audience? It seems not. So in that case, let us thank our speaker again.
Thank you. Thank you very much.
And thank you all for joining. And with